This conference will now be recorded.
Very good evening, students. So today we'll be concluding this chapter, magnetic effect of current. So we have already discussed the other part. We have already discussed atomic magnetism, moving coil, galvanometer theory part. So today what we'll do, we'll just learn about the conversion of galvanometer into an ammeter and conversion of a galvanometer into a voltmeter, and we'll solve few numerical problems which are being asked in various previous year's questions like JEE, NEET, etc. So if we want to use a galvanometer, as an ammeter, what we should do? Can we use the galvanometer directly in the circuit for measuring the current in a circuit? Or in other word, can we use the galvanometer directly as an ammeter? Answer is no. So there must be some modifications to be made in the galvanometer. So we'll see what kind of modifications we should do and what is the underlying theory in that. Okay, so what is the underlying theory for making, or what is the underlying concept in making a galvanometer or converting a galvanometer into an ammeter? So as you know, we use, suppose I have a circuit, I have some electric bulb, some kind of uh, appliances having resistors and many things. Okay, maybe I'm just taking two things, and just I have a battery, DC battery, and I want to measure the current in the circuit. Suppose I know this has some 100 ohm, this is some 500 ohm. So I need to measure the current through it, some voltage, some maybe 12 volt. So if I want to measure the current in the circuit, so what we should do? We should use an ammeter, and that ammeter has to be connected in the circuit in series combination. Okay, so we have to use that in series combination ammeter. So in case of galvanometer coil has certain resistance, isn't it? So galvanometer coil has certain resistance. So if we use the galvanometer as ammeter, since it has resistance, appreciable amount of resistance, so that may change the current in the circuit itself. Suppose in this case, suppose now generally ammeter for an ideal ammeter should have zero internal resistance. Okay, zero internal resistance. What does that mean? So if this is the case, zero internal resistance for an ammeter, then what will happen? If suppose the current is I in this circuit, so the whole current will pass through the ammeter. Whole current should pass through the ammeter. See, otherwise I will be using the measuring device and it will draw the current. Then what is the use? Okay, so there will be a loss of power, etc. So measuring device should not draw any power. Okay, that is the idea. Measuring devices should not draw any power. Okay, that is the point. So this is the motivation here. Measuring devices must not draw any power. Okay, so these are 2 points. Okay, so we have seen 3 things that actually ammeter is used. Ammeter is connected in series. So always ammeter is being connected in series to measure the current in the circuit. And the current does not get affected if these are the conditions. Okay, if measuring device doesn't draw any power, so to have that condition satisfied, the ammeter should have ideally zero internal resistance, or ideally zero resistance. But ordinary galvanometer is sensitive. Galvanometer is a sensitive one, but it has certain resistance. Galvanometer has certain resistance, and let us denote that galvanometer resistance as G. Resistance in the galvanometer coil. A resistance of galvanometer coil. Okay, galvanometer or galvanometer coil. So some resistance is there. So if we directly use this galvanometer as ammeter, ammeter obviously has a polarity that we have to take. So in that case, you know what will happen? The circuit current will be changed, but that we don't want. If we don't want that, then we have to make certain modifications such that the current in the circuit does not get affected by the galvanometer resistance. Okay, so we cannot use the galvanometer directly. We have to do certain modifications. Now let us see what is that modification we should make such that the current will not be affected. See, for that, you know what is done. See this figure. This is galvanometer. Okay, this is galvanometer. It has certain resistance G. So galvanometer is connected with a very small, okay, a very small resistance. S is connected in the parallel combination of parallel combination with not of parallel combination with with G. Okay, so this small resistance which is connected in parallel to this galvanometer is called shunt, when a very small resistance is connected, to any of the circuit in parallel, very small resistance connected in parallel is called shunt. So this is shunt. So therefore what I can say, that if we want to use a galvanometer as an ammeter, we have to use a shunt. Okay, we have to connect a shunt. So look, what will be the current, like what should be the value of the shunt? See, galvanometer resistance, you have made the galvanometer, you know the galvanometer parameter. That means you know how much current Ig. So this is the current through the galvanometer. I'll tell you how you should take this current through galvanometer. Okay, and G is the resistance, you know that resistance of the galvanometer. See how we should take this galvanometer current. Actually, see, in general, when you see in the laboratory, galvanometer will be like this. There will be a scale. Okay, there will be a scale, and there will be a panel like this. Okay, so you will see the number here. So you see the deflection, right? You see the deflection of this pointer either in the left hand direction or right hand direction. So current, when a current pass through the galvanometer can give the maximum deflection. Okay, that is called galvanometer current. So galvanometer current is the minimum current. So this is the, actually this is minimum current. This is the minimum current. Minimum current through the galvanometer which gives the maximum deflection. The maximum deflection, or it is called full scale deflection. It is called full scale deflection. Gives the full scale deflection. Full scale deflection. So galvanometer current means it can give the full scale deflection. Sometime maybe in the problem, maximum deflection can also be seen. So full scale deflection of the pointer. Okay. So this is the minimum current which is required for full scale deflection. So Ig, that is galvanometer current that is passing through the galvanometer, right? And that is the current, which minimum current through the galvanometer which can give full scale deflection. Okay, these are few things. So one more point I would like to say about this circuit. So I'll just erase this part to derive the numerical part. Okay. Okay, so we have seen few things like galvanometer resistance, galvanometer current we have understood. Now see what you see in this figure. See, this is actually inside the black box. What is happening inside this is black box. We cannot see anything here. What we see is this current. This current enters into the ammeter, and also it comes out in the, like, through the ammeter. So this is the current in the circuit, mains current or current in the circuit. So this I is current in the circuit. So suppose this, so this is a current. I enters and I leaves from or passes through ammeter. So this is what we see, and this is actually called the range of. See, this is actually the range of ammeter 0 to I. This is a range of ammeter. So range means the maximum current. The range means minimum to maximum. Minimum is 0 and maximum. So range of the ammeter. Sometime in numerical problem there will be this word range of ammeter. So that means you have to find out the circuit current. Range of the ammeter means you have to find out the circuit current, and then you have to write that 0 to that much. Suppose I is 5 ampere, so the range of this ammeter is 0 to 5 ampere maximum. So this is the maximum current actually we have supposed. So when we construct construct an ammeter, we actually set a range in the ammeter, how much maximum current it can measure. Minimum is taken as 0. So considering that we make galvanometer, sorry, ammeter out of galvanometer. Okay, so I have to use such a shunt that the ammeter range becomes 0 to I. I hope it is clear to you. So Ig is the galvanometer current. That means if the total current in the circuit is I, out of this I, Ig will pass through the galvanometer. Ig will pass through the galvanometer. So rest of the current will pass through the shunt. Okay, rest of the current will pass through the shunt. See, as I was mentioning that current should not get disturbed, or current should not, like, this galvanometer should not modify the current in the circuit, like ammeter should not modify the current in the circuit. See, because we have used this as shunt has very negligible resistance, some 0.1 ohm or sometime milli ohm maybe. So very small current is taken. Okay, very small, sorry, very small resistance is taken as shunt. That means the maximum current in the circuit will pass through the shunt, maximum current, and very negligible current will be passing through this, so that there will be no voltage drop, like in the sense there will be no much drop across this ammeter also. Okay, so power loss will not happen and current in the circuit will not get modified. Okay, so now let us see what should be this S to make the ammeter of range 0 to I, when I know the galvanometer resistance and galvanometer current. So look here, this is a parallel combination of the circuit, say parallel combination of resistors. So in that case, you know, the voltage across both the galvanometer and the shunt will be the same. So I can write Ig, which is passing through the galvanometer, into the G. This is voltage drop across the galvanometer, and that is same as the voltage drop I minus Ig, which is passing through the shunt, is this. Okay, so from here, if galvanometer current and galvanometer resistance and shunt is given, then you can find out the range. If the range is given and you have been given Ig and G, then you can find out the required S. So now we just want to find out what is the required resistance. So S will be given as, see, I have Ig once again. So here Ig. Okay, so S will be Ig by I minus Ig into G. Okay, so this is the thing. So I can find out the resistance. So from this one, okay, from this particular concept, we can actually make uh, see, I'll just erase this part. I hope this is clear to you. I have discussed the range of the ammeter also. Okay, so look, I have got this equation. This is master equation in this case. This is G actually. Then I get I minus. So suppose I have to calculate galvanometer current. How to find out that? So IGC, this I can bring this part left hand side. Okay, so this will be I into S. So from here we will be able to find out Ig is equal to I divided by G plus S into S. If I want to find out what is I, then I have to do this Gs plus G plus S divided by S. Okay, from here. So I can sometime see according to the problem we can do into Ig. Okay, like this. And see here, since ammeter is shunted with a very low resistance, its effective resistance will be effective resistance. See, effective resistance in this case, effective resistance is or equivalent resistance will be multiplication by summation of this. So it will be actually much lesser than even shunt. Okay. So we can see not only in case of galvanometer, in other cases also shunt is being used to uh, increase the range of the ammeter. Okay, anyway, so we have used here to protect the galvanometer first of all. Second thing, to convert the galvanometer into ammeter, etc. Okay, now we'll just move on to the other part, that is how to convert an ammeter into a galvanometer into a voltmeter. Yeah, there will be some problem. See, there will be parameters given for ammeter and some minimal parameter will be given for galvanometer. So sometimes they directly may ask ammeter, parameters of ammeter will be given. You have to find out parameters of voltmeter. Okay, sometimes this also be asked. Okay, so we'll just see how to convert a galvanometer into a voltmeter. So to convert a galvanometer into a voltmeter, you have to use a large resistance in series with the galvanometer. Galvanometer, as you see in this figure. So you have to use a very large resistor. Actually, resistance is greater than G. Large resistance in series with galvanometer. Okay, a large resistor you have to use. So actually, as I was saying, that voltmeter is a measuring device, so the potential difference across its endpoints should be very small, right? A voltmeter is a measuring device for measuring potential difference. Okay, voltmeter is used. Say if I have a circuit, okay, some other applications, okay, some other. So I have a battery here. So this is circuit. So if I want to measure the voltage across this bulb, so what I have to do? I have to bring a voltmeter and just place across this. So this is what is the use of voltmeter. I can just connect in parallel to this. Okay, any part of the circuit, any two part of the circuits. Okay, so actually voltmeter is a measuring device. It actually measures, voltmeter measures potential difference, potential difference between 2 points in the circuit, between 2 points in the circuit. Okay, so you look here, in this case, see, since it is connected in parallel with the circuit, the potential difference is intended to measure here. So as a result, a small part of total current pass through the voltmeter. Actually, very small part of current should pass through this. Very small part of the current should pass through this. Okay, such that the current will not be drawn too much by the voltmeter. This is the idea actually. This is the motivation. So to decrease the consumption of current, or to avoid the drawing of current by the voltmeter in general, and also at the same time it should give the proper reading, the internal resistance of a voltmeter, resistance, or its own resistance, internal resistance of a voltmeter, an ideal voltmeter, you can say, an ideal voltmeter is infinite. Okay, infinite internal resistance, so that very negligible current passes through this, but at the same time, say, voltage difference, or voltage means I into R, right? So if R is infinity, even if a very small current is flowing through that, it will give appreciable or measurable amount of reading. Okay, so this is one thing. So to make the resistance of the galvanometer very large or infinite, ideally we should connect a very large resistor in series with the galvanometer. As you see, this is the galvanometer, and along with that a very large resistance is being connected in series with the galvanometer. Now in this case, since it is series circuit, we know the we have to actually take care of few things when we construct a measuring device. We should have some range. So minimum range will be 0 and maximum range will be V, some voltage. Okay, if V is the voltage drop across this combination, then that will be actually the range, maximum range, 0 to V. Okay, this is the range. So this range, this voltage is actually given by I into R plus G, right? So if the range is given, maximum range is given for the meter, or if I know that suppose I have to make a voltmeter in the range 0 to 20, then I know this parameter. This is Ig, as you know, this is Ig. Ig is the current through the galvanometer, and since it is like resistor R is connected in series with galvanometer, same current will pass through both. So R plus G into Ig, this will give you the range of the voltmeter. So if you know this galvanometer resistance and the allowed current through the galvanometer, then you can easily find out the required resistor or resistance of the resistor, okay, using this. Okay, so suppose I want to find out, so V by Ig minus G, so this will be actually R, V by Ig minus G. So this will be the resistance required to connect with the voltmeter, sorry, to the galvanometer, to convert the galvanometer into voltmeter. Okay, so in this case actually the effective resistance, as you see, effective resistance, equivalent resistance, this is R plus G, which is actually much greater than G. Okay, this is another point. Okay, so in this case, by just increasing this part, this resistance, we can actually make the range more or less, or we can increase the range or decrease the range just by increasing or decreasing the resistance R. Okay, now we'll try to solve few numerical problem on this concept. Okay, so let us go ahead. So there is a problem here, numerical problem. See, a moving coil galvanometer of resistance 100 ohm is used as an ammeter using a resistance, that means shunt is also given. So here if I draw galvanometer, so shunt is given, so the galvanometer resistance is given, G is 100 ohm and S is given as 0.1 ohm. Now let us read the next part. The maximum deflection current, as I said, maximum deflection current or full scale deflection current means the minimum current which is required for maximum deflection, that is actually Ig. Galvanometer current is given 100 microampere. So Ig is given. So Ig is this. Okay, Ig. So the maximum deflection current in the galvanometer is 100 ohm. Sorry, 100 milliampere. Microampere, sorry. 100 microampere. The minimum current in the circuit so that the ammeter shows maximum deflection. So what is the question asking? What you have to calculate? What is the current in the circuit? If you look here, what is the current in the circuit? The current in the circuit is I. Okay, so here current in the circuit I, which we have to actually calculate. So what was the formula? See, this S is given. See here, I is equal to G plus S divided by S into Ig. We'll just use that. Somebody can directly use like right from here itself without remembering the formula. How to do that? I into S is equal to, I'm sorry, this is I minus Ig into S is equal to Ig into G. Okay, so I have to find out see this part. So let us say Is and see Ig G plus S. Okay, so I have to find out I, right? So we have to divide this with S. So this. So look here, Ig is given as 100 microampere. Let me write this as 6 ampere, minus 6 ampere, and G plus S. So G plus S. So G plus S is this much. That means 100. This is 100, not 1, divided by S is 0.1. So if you calculate, this current will be, let us do that. See, this is 0.1. Okay, so this into 10 to the power minus 6 into 1. So see, this will actually cancel 3 of them. This power will be then 10 to the power minus 3. Therefore, what you get, this is in ampere. In ampere, so it will be actually 100.1 milliampere. So this is the current required for maximum deflection in the galvanometer. So this is the answer. Okay, so I hope it is understandable. Now we'll just go to the next problem. This is actually an elaborate problem, and also this is sometime in AIMS exam it was being asked. So a galvanometer has a current sensitivity. See, in the previous day we had learned current sensitivity. What do you mean by current sensitivity? Current sensitivity Is is written as deflection per unit current. So in this case it is written, see, galvanometer. A galvanometer has a current sensitivity 1 milliampere per division. That means 1 division represent 1 milliampere current. This is what it is. Okay, it is given as this. So 1 division represents 1 milliampere current. Okay, this part is clear. So current sensitivity of the galvanometer is 1 milliampere per division. That means 1 division. So deflection of 1 division means the current will be 1 milliampere. A variable shunt is connected across the galvanometer. I'll draw the figure. Before that, let us read that. A variable shunt is used So a variable shunt is used. Across the galvanometer. How it is used? Across the galvanometer. Across the galvanometer, a variable shunt is being used. Okay. See, and the combination is put in series with a resistance of 500 ohm and cell of internal resistance 1 ohm. See, I think I'll just draw this figure, then you will be able to visualize. So I have a galvanometer. Okay. So which has current sensitivity given. Okay. So this galvanometer is connected with a shunt, a variable shunt. See, this is variable shunt. Across it, that means parallel. Shunt means parallel, as we have already discussed. This is shunt. Okay, variable shunt. Now this combination has been put in series with 500 ohm resistance. Okay, and a cell of 1 ohm internal resistance. See this cell of internal resistance for 1 ohm. So this is R, let us say this is 500 ohm. This is the cell which has EMF E, say, and this is the internal resistance small r. Current which is passing through the galvanometer is Ig. Okay, so this much is okay. Now the question is, it gives deflection of 5 divisions for shunt. Since the shunt is variable, I can change the shunt value of the shunt. So when the shunt is changed, is S and then deflection 5 is noted. So when 5 ohm, then division, how much? So it is in division. Okay, divisions, 5 divisions. That means it is equivalent to how much current? This current will be actually galvanometer current. Okay, so this will be galvanometer current. Okay, so division, so deflection directly related to galvanometer current. So Ig will be how much? See, sensitivity of the galvanometer was given. So what was that? That one division represents 1 milliampere current. So here Ig will be found. See, when the shunt is given as 5, deflection is 5 divisions, so 5 milliampere is the current, because per division deflection represent 1 milliampere current. Second observation, this is first observation. Second observation says, when the shunt is 25 ohm, then 20 divisions of deflection is being seen. Okay, so that means what is the current? 20 milliampere is the current. Okay, per division 1 milliampere, so 20 divisions 20 milliampere. So this is actually the observation. Now the question is, what is the EMF? EMF of the cell is how much voltage out of this port? The question says that there is a galvanometer whose sensitivity is 1 division per milliampere current. That galvanometer is shunted with variable shunt, and the combination of the shunt and the galvanometer is connected in series with a resistor and a cell of internal resistance 1 ohm. This is 1 ohm. Okay, this is 1 ohm, 500 ohm. So there are two observations: when the shunt is 5 ohm, then 5 divisions, or galvanometer current is 5 milliampere. When 25, then the galvanometer current, I'm sorry, this is not galvanometer current. The current, galvanometer, this is not the galvanometer current. This is actually the main current in the circuit. I'm sorry, this is current in the circuit. Current in the circuit is being seen like this. Okay, current in the circuit is seen I, right? So I is sometime 5 milliampere, sometime 20 milliampere. Okay, I'm sorry. So we should not make mistake in understanding. Before we solve the problem, we have to understand the problem. So that's why you are just reading the problem again and again. That would help us. So this current is actually the main current circuit in the main circuit. Current in the main circuit. Okay. Now we have to find out what is the value of E. This is the question here. I'll just draw the figure briefly here. See, I have a galvanometer, then I have variable shunt, then this is connected to a resistor and cell with internal resistance small r or 1 ohm. This is small r, this is capital R, this is E, this is having G, this is S. Okay, this is the circuit. So what are the observations? We have already we have found out observations. So we know you know what will be the circuit current, circuit current. The circuit current will be I is equal to, see, if I just take this combination as a single resistor, then EMF divided by R plus small r plus the resistance of this combination S and G. So G into S divided by G plus S, right? So this is actually the current in the circuit. Now I have two observations and two times I'll just put the value. See, according to the question, I'll write here, according to the question, what are given? 5 ampere or 5 deflection will be 5 milliampere when this is 5 ohm. Okay, look this here, 5 ohm shunt, right? So let us do a little bit of simplification here. Okay, so I think again, sorry for this. This current, since it is directly depending on the, like it is showing the deflection, I was initially correct that this will be actually galvanometer current. Okay, this will be actually galvanometer current, which is seen because the division is, it is actually related to galvanometer sensitivity, so that's why these currents are actually galvanometer current. Okay, so just excuse me for this misinterpretation. Okay, anyway, so now say we can actually make a little bit of simplification here. So this will be G plus S is R plus R, G plus S plus G into S. Okay, now Okay, so we know Ig could be obtained as I into S divided by S plus G. If you remember the formula, see in case of ammeter, I is Ig is I into S divided by G plus S, right? So in the problem, in this given problem, actually this is given, okay? Because every time when shunt is changed, the deflection is changed. So that's why the current through the galvanometer actually is changing. Current through the galvanometer is changing. That's why the deflection is changing. Okay. Since shunt is changed, galvanometer current is changed, and also the deflection changes. So we'll just put this value of I over here and see. Let us do a little bit of simplification after doing that. Okay, so this is R plus R into G plus S, G plus S into GS. This is actually I into S by S plus G. This. So this will cancel each other. So Ig, galvanometer current, is expressed now in terms of the given parameter plus GS. Okay. Now if we take the first observation, 5 ohm shunt, then 5 milliampere current, Ig. So 5 milliampere Ig, then she will put this here. So 5 into E divided by R plus small r, we can just write it down directly. So R plus R, small r is how much? Small r is 1 ohm, capital R is 500 ohm. Okay, so this is 500 ohm. So this is 500 plus, sorry, plus 1, that is 501. G plus S, we don't know what is G. Let us write G like this, and S is 1. Okay, then further, oh sorry, S is fine. So 5 here. S is 5. S is 5. Then plus G into S. So 5 into G. This is equation number 1. Now we have 20 milliampere current. 20 milliampere current for 25 ohm shunt. So 25 into this divided by, again this factor is G plus 25 plus 25 into G. Okay, if we take ratio, or somehow we have to actually find out the unknown resistance, unknown quantity here. See, if we take the ratio, then EE will cancel each other. So only thing what we will be able to find out from here is G. So G could be found out 88.2 ohm. So this is first thing which we have to calculate here. So once we know that, then we actually will be able to find out the EMF. We can use in the equation using G equal to 88.2 ohm in equation 1. See, equation 1 will be able to find out. See, 5 amperes is this 5 get cancelled. So 10 to the power minus 3 is equal to E divided by 500 501. That is as good as 500 only. So this is 88.2 plus 5 divided by 80, sorry, plus 88.2 into 5. Okay, So this is the thing. So if we just do the calculation, so we'll be able to easily find out that this will be 47.1. Okay, ohm. I'm sorry, this is not ohm. This is volt. Volt. EMF is in volt. Sorry. So I think I'll stop it here for today. Next day we'll start with the magnetism part. Magnetism and matter. Okay, matter and magnetism. Okay, so there we'll take up also numerical problems. Anyway, so thank you for your patience. Bye for today.